Hello all, welcome to the lecture. In the last lecture, we started discussing electron spin resonance spectroscopy or ESR spectroscopy. We saw that the primary condition to obtain an ESR signal is the presence of an unpaired electron. So, the primary condition is the presence of an unpaired electron. We looked into the energy level diagram. So, in the last class we talked about the energy level diagram and also discussed some important parameters of the ESR spectrum. So, the parameters that we had discussed are, we discussed intensity, then we discussed the width of the spectrum and we also discussed about the peak position. So, in today's lecture, we would consider the origin of the hyperfine structures. So, today we will talk about the origin of the hyperfine structures. So, let us start by considering the simplest system. So, what is the simplest system? The simplest system that we will consider to start with is the hydrogen atom. So, this is the simplest system because the hydrogen atom contains one electron. And because it contains one electron, thus the electron has to be unpaired. So, we would expect only one ESR line. So, our expectation is only one ESR line, and we expect just one ESR line because we are talking about only one electron in the hydrogen atom. But if we look into the experimental results, so these experiments predict that the ESR signal of this hydrogen atom consists of two closely spaced lines. So, now you may ask, instead of one, how come we have two closely spaced lines? And this has been explained in terms of interaction between the electron spin and the nuclear spin. So, there is interaction between the electron spin and the nuclear spin, and this interaction has been termed as hyperfine interaction. So, now if we consider the electron as particles, it is difficult to think of interaction of the electron with the nucleus. So, this is because if electron is considered as a particle, this interaction is difficult to think about because the nucleus is far away from the electron. But quantum mechanics tells us that the electrons can be considered as waves, and these waves can be represented by a wave function. So, let us say psi. So, it is known that for s orbitals. So, if you think about s orbitals, so in terms of wave functions we can write psi 1 s or psi 2 s if we consider the 2 s orbital. So, there is a finite non-zero value of psi at the nucleus. So, these s orbitals they have finite non-zero value of psi at the nucleus. However, for other orbitals, for example, if we consider the p orbital or if we consider the d orbital. So, these orbitals have a value of 0 at the nucleus, because these orbitals at the nucleus have a node. So, it has a value of 0. So, thus if the free electron is in an s orbital, it can actually interact with the nucleus, and for other orbitals like d or p orbitals, this interaction will not be possible. So, in the case of this hydrogen atom, we know the electron for the hydrogen atom resides in the 1 s orbital, and because it is in the 1 s orbital, thus this hyperfine interaction is possible. So, again this hyperfine interaction is the interaction between the electron spin and the nuclear spin. So, the strength of this interaction is denoted by a parameter A. So, we will write A, where A is the strength of the interaction, and this A is known as the hyperfine coupling constant. So, this hyperfine coupling constant A stands or gives us the strength of the interaction, and the unit of A is the same as the unit of frequency. So, the interaction energy is given by the expression A m I m s h, where A is the hyperfine coupling constant, m I comes from the nuclear spin and m s comes from the electron spin. So, for hydrogen atom we have one proton in the nucleus, and for a proton we know that I equals half, and because I equals half, that means m I can take two values. So, m I can be plus half or minus half, and let us say the electron is in the beta state. So, beta state means the down spin state, that means m s equals minus half. So, if the electron is in the beta state, this electron can interact with both m I equals plus half and m I equals minus half. In other words, if we write it pictorially, this m s equals minus half can interact with m I equals plus half and m I equals minus half. And so, we can actually calculate the energy. So, now if we put A m I m s h and let us say that m I equals plus half and the electron is in the beta state. So, m s equals minus half, then we have the energy that is minus A h by 4. In other words, for interaction between an electron in the beta state with m I equals plus half, there will be a negative energy. So, now let us consider all the possible interactions and draw a schematic energy level diagram. So, let us look into the energy level diagram. So, our vertical axis is the energy axis and we have two states, alpha that is the upspin state and beta that is the downspin state, and these two states are degenerate when there is no magnetic field, that is B equals 0. However, when we have an externally applied magnetic field, that is B is not equal to 0, then we have interaction of the electron spin with the magnetic field, and because of this interaction the degeneracy which was there at B equals 0 is lifted, and now we have two states. One is alpha, which is the higher energy state, that is the upspin state, and the other is beta, which is the lower energy state, or this is the downspin state. Now, in alpha we know that m s equals plus half, and for beta m s equals minus half. And if we look into the energies of these states, the beta state has energy half G s beta b, and the alpha state has energy that is minus half G s beta b. So far, we have not considered the interaction of the electron spin with the nuclear spin, or in other words, we did not consider the hyperfine interaction. So, now if we consider the hyperfine interaction, then these energy levels will further split. So, because m I can take two values, so we will have 4 levels here, and let us put the m I values here. So, here m I equals plus half for the lowest level and m I equals minus half, and for the highest level m I equals plus half, and for the second highest level, that is the lower level for the alpha spin interaction, m I equals minus half. So, what we can see here, we have 4 levels, and now let us put down the energies. So, the energy here, so this is half G s beta b, and then the hyperfine interaction energy is given by A m I m s h. For this case, this is m s equals minus half, m I equals plus half. So, if I multiply minus half times plus half, we get minus 1 by 4. So, here it is minus A h by 4. Similarly, for this level it is half G s beta b, but then now we are multiplying minus half, which is m s, and minus half, that is m I. So, we get plus A h by 4. So, we can think that we had the energy before the hyperfine interaction, that is half G s beta b, and now it splits. So, one level goes up by A h by 4 and the other level goes down by A h by 4. So, we have half G s beta b minus h by 4 and half G s beta b plus h by 4. And for the other two levels we can write this is minus half G s beta b. So, this is the highest level. Then we are multiplying plus with plus. So, we have plus A h by 4, and similarly the other level has minus half G s beta b minus A h by 4. So, this is our energy level diagram. Now, if we see, we can see we have 4 energy levels. This is one, this is the next one, this is the third one, and this is the fourth one. And because of this hyperfine interaction, so instead of 2, now we have 4 energy levels. And because we have 4 energy levels, we can expect more than one transition that is possible. So, let us try to draw randomly 4 energy levels, and let us say there is no rule which would restrict us from having any transition. So, I can have transition from here to here, here to here, here to here, here to here. So, you can see there are many transitions that are possible, and in fact, if we see here, the number of possible transitions is actually more than 2. However, from experiments we know that the hydrogen atom shows only 2 ESR signals. So, at this point we need to understand why instead of many ESR lines for hydrogen atom, we have only 2 lines in the spectrum. So, at this point we need to focus what is known as the selection rule for ESR transitions. And the selection rule for such transitions states that the value of m I should not change. So, if the m I value does not change, so what are the different transitions we can have? So, we have m I equals plus half and we also have m I equals plus half. So, this is one possible transition, and the other possible transition is m I equals minus half and m I equals minus half. So, this is the other possible transition. So, these are the only 2 possible transitions that we have. So, we have one transition which is of larger energy, and we say this is number 1, and we have another transition which is of smaller energy difference, this we label as number 2. So, now let us look into this energy differences or the transition energies. So, if we look into one, that is from m I equals plus half to m I equals minus half, then the energy involved in the transition is given by h nu equals G s beta b plus A h by 2. So, this h nu is the energy, but if we want to know about just the frequency, then we have to divide it by h. So, nu equals G s beta b divided by h plus A by 2. So, this energy difference is for the process 1, that is m I equals plus half to m I equals plus half. Now, if we think about the process 2, then what we have? We have h nu equals G s beta b minus A h by 2, or in other words nu equals G s beta b divided by h minus A by 2. So, now if we compare these two transitions, we can see that the energy difference, that means the energy difference between 1 and 2 is nothing but A, because let us say we write this as h nu 1, that is nu 1, and h nu 2, that is nu 2, and what we do is let us say nu 1 minus nu 2. So, what we get here? We have G s beta b divided by h plus A by 2 minus G s beta b divided by h minus A by 2, and if you do this difference, the G s beta b cancels out, and so what we get here is A. So, we can see that if we compare these transitions, these two transitions are separated by A. So, what does this mean in terms of a spectrum? So, this means let us say this was my energy G s beta b divided by h, and because ESR is shown as first derivative plots or the first derivative of the peaks. So, we will have one peak here and we will have another peak here, and such that this difference is A by 2 and this difference is also A by 2. In other words, what it means, the difference from one peak to another peak is A. So, this brings us to the end of the lecture, and in the next lecture we would look into more details of the ESR spectrum.